Welcome, cosmic explorers. Have you ever gazed at the night sky and felt that deep, ancient pull of wonder? For thousands of years, we humans have looked up, trying to piece together the grand puzzle of where we came from and what our place is in this incredible universe. From the captivating myths our ancestors told to explain the stars, to the brilliant minds who dared to challenge everything we thought we knew, our journey to understand the cosmos has been nothing short of amazing. Join us as we journey through time, discovering how our understanding of the stars, planets, and everything beyond has completely transformed, moving us from Earth-centered ideas to a universe governed by astonishing scientific laws. Get ready to see the cosmos through fresh eyes and have your mind truly blown. From the dawn of humanity, we have gazed upon the night sky with a sense of awe and wonder. The celestial tapestry, woven with glittering stars and luminous nebulae, has captivated our imaginations for millennia. How did this magnificent universe come to be? What is our place within this cosmic expanse? These fundamental inquiries have driven us to explore the cosmos, seeking answers that lie hidden among the stars. The pursuit of these answers has led us on an extraordinary journey of discovery, a quest we call cosmology, the study of the cosmos. Our ancestors, seeking to make sense of the world around them, crafted intricate myths and stories to explain the origins of the universe. As human societies developed, so too did our understanding of the universe. The ancient Greeks, driven by an insatiable thirst for knowledge, embarked on a quest to unlock the secrets of the universe. They meticulously observed the movements of celestial objects, charting the courses of stars and planets across the night sky. Among these pioneering thinkers, Aristotle emerged as a towering figure whose ideas would shape Western thought for centuries. Aristotle envisioned a geocentric universe, a cosmic model that placed Earth at the center of all creation. This geocentric view, with Earth as the focal point of the cosmos, resonated deeply with the human experience, reinforcing our sense of place and purpose in the grand scheme of the universe. However, as centuries passed and new technologies emerged, cracks began to appear in this seemingly unshakable cosmic framework. The 16th century ushered in an era of unprecedented intellectual and scientific ferment, a period we now call the Scientific Revolution. At the forefront of this revolution was a Polish astronomer named Nicolaus Copernicus, who dared to challenge the geocentric model that had dominated Western thought for centuries. In his groundbreaking work, De Revolutionibus Orbium Coelestium, Copernicus proposed a radical new model of the universe, a heliocentric model. This revolutionary idea placed the Sun, not Earth, at the center of the solar system, with our planet relegated to the status of just another celestial body orbiting the Sun. Galileo Galilei, an Italian astronomer, made groundbreaking observations with his newly invented telescope, providing compelling evidence in support of the heliocentric model. The shift from a geocentric to a heliocentric perspective not only revolutionized astronomy, but also laid the groundwork for the development of modern science. The scientific revolution, with its emphasis on observation, experimentation, and mathematical reasoning, transformed our understanding of the natural world. One of the most influential figures in the history of physics was Sir Isaac Newton, an English mathematician and physicist, whose groundbreaking work laid the foundations for classical mechanics and gravitation. In his masterpiece, Philosophiae Naturalis Principia Mathematica, Newton unveiled his law of universal gravitation, a fundamental force that governs the interactions between objects with mass. Newton's law of gravitation provided a powerful explanation for the motions of celestial bodies, demonstrating that the same force responsible for an apple falling from a tree also governs the orbits of planets around the Sun. This profound insight unified the terrestrial and celestial realms, demonstrating that the universe operates according to a set of universal laws. It is a journey that continues to this day, as we strive to unlock the secrets of the cosmos and unravel the mysteries of our existence. Long before the advent of telescopes and the scientific method, our ancestors sought to make sense of the cosmos through the power of myth and storytelling. Nearly every ancient culture developed its own unique cosmogonies, myths and legends that explained the origin of the universe, the earth, and humanity. In many ancient cosmologies, the universe was seen as the creation of powerful deities or cosmic beings. The ancient Egyptians, for example, believed that the god Atum emerged from the primordial waters of Nun and created the world through a series of emanations. Similarly, in Norse mythology, the giant Ymir was formed from the melting ice of Niflheim, and the gods Odin, Vili, and Ve created the world from his body. These creation myths, though often fantastical and symbolic, reflect a deep human desire to find meaning and order in the vastness of the cosmos. Amidst the rich tapestry of ancient cosmologies, a distinct shift in perspective emerged in ancient Greece. Greek philosophers, renowned for their emphasis on reason and observation, began to move away from purely mythological explanations and sought natural, rather than supernatural, accounts of the cosmos. One of the earliest Greek philosophers to grapple with questions of cosmology was Thales of Miletus, who lived in the 6th century BCE. Thales is said to have believed that water was the fundamental element from which all things originated. Following Thales, other Greek philosophers continued to explore the nature of the cosmos, proposing a variety of models and theories. The Greek philosophers' emphasis on reason, observation, and the search for natural explanations laid the groundwork for the development of Western science. Among the Greek philosophers who grappled with the nature of the cosmos, Plato and Aristotle stand out as towering figures whose ideas profoundly influenced Western thought for centuries. Plato, a student of Socrates, believed in a realm of perfect, unchanging forms that transcended the physical world. In his dialogue Timaeus, Plato describes a universe created by a divine craftsman, the demiurge, who fashioned the cosmos according to these eternal forms. Plato envisioned a spherical Earth at the center of the universe, surrounded by a series of concentric spheres representing the sun, moon, planets, and stars. Aristotle, Plato's most famous student, developed a more complex and nuanced model of the universe, building upon his predecessor's ideas while incorporating his own observations and philosophical insights. Aristotle's model of the universe, with its emphasis on Earth's central position and the perfection of the celestial realm, became the dominant cosmological view for nearly 2 millennia. While the geocentric model of the universe, championed by Aristotle and Ptolemy, held sway for centuries, it was not without its critics and inconsistencies. One such dissenting voice was that of Aristarchus of Samos, a Greek astronomer who lived in the 3rd century BCE. Aristarchus proposed a heliocentric model of the universe, suggesting that the Earth and other planets revolved around the Sun. Another challenge to the Aristotelian model came from the observation of certain celestial phenomena that were difficult to reconcile with the idea of perfectly uniform circular motions. For example, the apparent retrograde motion of planets, the periodic reversal of their movement across the sky, posed a puzzle for astronomers seeking to fit observations into the geocentric framework. Despite these attempts to reconcile observations with the geocentric model, the seeds of doubt had been sown. The ancient philosophers and astronomers, from the myth-makers to the Greek thinkers, left an indelible mark on our understanding of the cosmos. While their models and theories may seem simplistic or flawed in retrospect, they represent a crucial stage in the development of human thought. The ancient Greeks, in particular, deserve credit for shifting the focus from supernatural explanations to natural ones. Their emphasis on reason, observation, and the search for underlying principles marked a departure from the mythological cosmologies that preceded them. The legacy of the ancients is not merely one of specific models or theories, but of a questioning spirit, a thirst for knowledge, and a willingness to challenge established dogma. The journey of cosmological exploration, initiated by our ancestors, continues to this day, driven by the same insatiable curiosity that inspired those who first dared to look up at the stars and wonder. The heliocentric revolution. Copernicus challenges the cosmos. As Europe emerged from the Middle Ages, a profound intellectual and cultural transformation began to take shape, known as the Renaissance. This period of renewed interest in classical learning and a spirit of inquiry set the stage for a revolution in scientific thought. It was a revolution that would challenge long-held beliefs about the universe and our place within it. At the heart of this revolution was a Polish astronomer named Nicolaus Copernicus. His groundbreaking ideas would forever alter our understanding of the cosmos. Copernicus, born in 1473, lived in a time when the prevailing view of the universe was still largely shaped by the geocentric model proposed by Aristotle and refined by Ptolemy centuries earlier. This model, with Earth firmly positioned at the center of all creation, had become deeply entrenched in both scientific and religious thought. However, Copernicus, through his meticulous observations and mathematical calculations, began to question the validity of this Earth-centered view. In the early 16th century, Copernicus began developing his own model of the universe. This model dared to challenge the prevailing dogma. He proposed a heliocentric system, placing the Sun, not Earth, at the center of the solar system. In Copernicus's model, Earth was relegated to the status of just another planet, orbiting the Sun along with Mercury, Venus, Mars, Jupiter, and Saturn. This revolutionary idea, though not entirely new, Aristarchus of Samos had proposed a heliocentric model centuries earlier, was a radical departure from the accepted wisdom of the time. Copernicus hesitated to publish his heliocentric theory, aware of the potential controversy it would ignite. It was not until 1543, shortly before his death, that his groundbreaking work, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, was finally published. This seminal work marked a turning point in the history of astronomy, ushering in a new era of cosmological thought and paving the way for the scientific revolution that would follow. The seeds of doubt sown by Copernicus's heliocentric model found fertile ground in the work of Galileo Galilei, an Italian astronomer who would become one of the most influential figures in the scientific revolution. Galileo, born in 1564, was a contemporary of Johannes Kepler, a German astronomer who refined Copernicus's model by demonstrating that planets move in elliptical rather than perfectly circular orbits. Galileo, however, is best known for his groundbreaking observations with the telescope, observations that provided compelling evidence in support of the heliocentric model and challenged the long-held belief in a perfect and unchanging celestial realm. In 1609, Galileo constructed his own telescope, based on designs he had heard of from the Netherlands. With his telescope, Galileo made a series of astonishing discoveries that would revolutionize our understanding of the cosmos. He observed mountains on the moon, revealing that celestial bodies were not perfectly smooth spheres as previously believed. He discovered 4 moons orbiting Jupiter, providing evidence that not all celestial objects revolved around Earth. And he observed the phases of Venus, a phenomenon that could only be explained if Venus orbited the Sun, not Earth. Galileo's observations, meticulously documented and widely disseminated, sent shockwaves through the scientific community and beyond. His discoveries provided compelling evidence in support of the heliocentric model, challenging the geocentric view that had dominated Western thought for centuries. However, Galileo's outspoken support for the Copernican system brought him into conflict with the Catholic Church, which considered the heliocentric theory to be heretical. In 1633, Galileo was summoned before the Roman Inquisition and forced to recant his heliocentric views. He lived out the remainder of his life under house arrest, his scientific work censored. Despite this persecution, Galileo's ideas continued to circulate, inspiring other scientists and helping to pave the way for the eventual acceptance of the heliocentric model. The scientific revolution reached its zenith in the late 17th century with the work of Sir Isaac Newton, an English physicist and mathematician whose groundbreaking contributions to physics, mathematics, and astronomy would lay the foundations for modern science. Newton, born in 1643, the year of Galileo's death, inherited a scientific world in transition, a world grappling with the implications of the heliocentric model and seeking a deeper understanding of the forces governing the universe. Newton's most celebrated work, Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, published in 1687, is considered one of the most important scientific works ever written. In the Principia, Newton laid out his 3 laws of motion, which describe the relationship between an object's motion and the forces acting upon it. These laws provided a unified framework for understanding motion both on Earth and in the heavens, demonstrating that the same physical laws govern the apple falling from a tree and the planets orbiting the sun. Perhaps Newton's most profound contribution to science was his law of universal gravitation, which states that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between their centers. This elegant law provided a precise mathematical explanation for the force that holds the planets in orbit around the Sun, the Moon in orbit around Earth, and the tides on Earth. Newton's work transformed our understanding of the universe, ushering in a new era of precision and predictability in the physical sciences. His laws of motion and gravitation provided a powerful framework for explaining a wide range of phenomena, from the motions of celestial bodies to the behavior of objects on Earth. Newton's universe was a clockwork universe, a vast and intricate mechanism governed by immutable laws, a universe that could be understood and predicted through the power of mathematics. The scientific revolution, spanning roughly from the 16th to the 18th centuries, stands as a pivotal epoch in human history, fundamentally reshaping our understanding of the universe and our place within it. This era of unprecedented intellectual ferment shattered long-held beliefs, replaced ancient dogmas with empirical observation and mathematical reasoning, and laid the groundwork for modern science. The scientific revolution was not merely a period of scientific discoveries. It was a profound shift in worldview. The geocentric model, with its Earth-centered cosmos and hierarchical structure, gave way to a heliocentric perspective, placing the Sun at the center of the solar system and relegating Earth to the status of just another planet. This shift in perspective had profound philosophical and theological implications, challenging humanity's perceived place in the grand scheme of creation. Beyond specific discoveries and theories, the scientific revolution instilled a new way of thinking about the natural world, a scientific method based on observation, experimentation, and the search for natural explanations. This empirical approach, championed by figures like Francis Bacon and René Descartes, replaced reliance on ancient authorities and revealed the power of human reason to unlock the secrets of the universe. The legacy of the scientific revolution continues to shape our world today. The scientific method, born out of this era of inquiry, remains the foundation of scientific progress, driving advancements in medicine, technology, and our understanding of the universe. The spirit of curiosity and the pursuit of knowledge, ignited during this transformative period, continue to inspire scientists and explorers across all disciplines, propelling us ever forward in our quest to comprehend the cosmos and our place within it. Unveiling the secrets of the universe. The scientific revolution, with its emphasis on observation, experimentation, and mathematical reasoning, provided a powerful toolkit for unraveling the mysteries of the universe. Armed with these tools, scientists embarked on a journey of discovery that continues to this day, a journey that has led us from the Earth-centered cosmos of the ancients to the vast expanding universe of modern cosmology. As telescopes improved, astronomers peered deeper into the cosmos, revealing a universe far grander and more complex than previously imagined. Galaxies, vast islands of stars, were discovered beyond our own Milky Way, stretching the boundaries of the observable universe to unimaginable distances. The discovery of the expansion of the universe, with galaxies rushing away from each other, hinted at a universe born in a cataclysmic event, the Big Bang. The development of new theories, such as Einstein's theory of general relativity, revolutionized our understanding of gravity, space, and time, revealing a universe where gravity warps the fabric of space-time, creating exotic objects like black holes and neutron stars. Quantum mechanics, another pillar of modern physics, unlocked the secrets of the subatomic world, revealing the strange and counterintuitive behavior of particles at the smallest scales. The journey of cosmological exploration is far from over. As our scientific tools and theories continue to advance, we delve deeper into the mysteries of the universe, seeking answers to fundamental questions about its origin, evolution, and ultimate fate. The quest to understand the cosmos is a testament to the indomitable spirit of human curiosity, a journey that continues to inspire awe and wonder, reminding us of the vastness of the universe and the boundless potential of human ingenuity. The cosmic puzzle. Hints of a beginning. As the 19th century progressed, advancements in physics and astronomy began to cast doubt on the long-held notion of an eternal and unchanging universe. The development of thermodynamics, a branch of physics that studies heat and its relation to other forms of energy, introduced a new concept that would have profound implications for our understanding of the cosmos: entropy. The second law of thermodynamics, formulated by physicists like Rudolf Clausius and William Thomson, Lord Kelvin, states that the entropy of a closed system always increases over time. Entropy, often described as a measure of disorder or randomness, suggests that the universe, if left to its own devices, tends towards a state of greater disorder and uniformity. This principle, when applied to the cosmos as a whole, suggested that the universe could not be eternal, as an infinite amount of time would have already led to a state of maximum entropy, a state of thermal equilibrium where no further change or activity is possible, often referred to as heat death. The implications of the second law of thermodynamics were profound. If the universe were truly eternal and unchanging, as the steady-state model proposed, it should have already reached a state of maximum entropy, a state of thermal and dynamic equilibrium. However, the universe we observe is far from being in such a state. Stars are still shining, galaxies are still evolving, and life, a complex and highly ordered phenomenon, exists on our planet. This discrepancy between the predictions of an eternal universe and the observed reality suggested that the universe might not be eternal after all. The concept of entropy, coupled with the growing body of astronomical observations, hinted at a universe with a beginning, a universe that had not always existed but had emerged from a state of lower entropy in the distant past. This realization marked a significant departure from the classical view of an eternal and unchanging cosmos, paving the way for the revolutionary ideas of modern cosmology. Expanding horizons, the discovery of an expanding universe. As physicists grappled with the implications of thermodynamics for the universe's fate, astronomers were making groundbreaking observations that would further challenge the prevailing cosmological view. The development of more powerful telescopes and new techniques for measuring distances to stars and galaxies allowed astronomers to probe the depths of the cosmos with unprecedented precision, revealing a universe far grander and more dynamic than previously imagined. In the early 20th century, an American astronomer named Vesto Slipher made a puzzling observation. While studying the spectra of light from distant galaxies, the unique fingerprints of light emitted by different elements, Slipher noticed that these spectral lines of many galaxies were shifted towards the red end of the spectrum, a phenomenon known as redshift. This redshift, analogous to the Doppler effect for sound waves, suggested that these galaxies were moving away from us. Building on Slipher's observations, Edwin Hubble, another American astronomer, made a groundbreaking discovery in 1929. Hubble, using a new telescope at the Mount Wilson Observatory in California, meticulously measured the distances to several galaxies and compared these distances to their redshifts. What Hubble found was astonishing. There was a direct relationship between a galaxy's distance and its redshift. The farther away a galaxy was, the faster it seemed to be receding from us. Hubble's discovery, now known as Hubble's law, had profound implications for our understanding of the universe. The observed expansion of the universe, with galaxies flying apart from each other like raisins in a rising loaf of bread, suggested that the universe was not static and unchanging, but rather dynamic and evolving. Moreover, if we were to rewind the cosmic clock, imagining the galaxies moving closer together instead of farther apart, it implied that there must have been a time in the distant past when all the matter and energy in the universe were concentrated in an extremely hot, dense state, a cosmic explosion now known as the Big Bang. The idea of a universe born from a cataclysmic explosion initially met with resistance from some quarters of the scientific community. The notion of a universe with a beginning challenged the prevailing view of an eternal and unchanging cosmos, and the idea of a cosmic explosion seemed almost too fantastical to be true. However, the converging evidence from thermodynamics, suggesting a universe with a beginning, and Hubble's observations of an expanding universe, pointing towards a primordial explosion, gradually led to the acceptance of the Big Bang theory as the most compelling explanation for the origin and evolution of our universe. The Big Bang theory, in its essence, describes the universe as expanding and cooling from an extremely hot, dense state approximately 13.8 billion years ago. In the first fraction of a second after the Big Bang, the universe was an unimaginably hot and dense soup of elementary particles and radiation, expanding and cooling rapidly. As the universe expanded, it cooled, and energy began to condense into matter, forming protons, neutrons, and electrons, the building blocks of atoms. As the universe continued to cool, protons and neutrons began to combine through nuclear fusion, forming the nuclei of light elements such as hydrogen, helium, and lithium. This process, known as Big Bang nucleosynthesis, is thought to have occurred within the first few minutes after the Big Bang, and is responsible for the relative abundances of these light elements observed in the universe today. Over hundreds of thousands of years, the universe continued to expand and cool, and electrons eventually combined with atomic nuclei to form neutral atoms, a process known as recombination. This event marked a crucial transition in the early universe, as it allowed light to travel freely through space for the first time, decoupling from matter and creating a faint afterglow of the Big Bang that we can still detect today, the cosmic microwave background radiation. One of the most compelling pieces of evidence supporting the Big Bang theory came from an unexpected discovery in 1965. Arno Penzias and Robert Wilson, two radio astronomers working at Bell Telephone Laboratories in New Jersey, were using a sensitive horn antenna to study radio waves from the Milky Way. As they meticulously calibrated their instrument, they noticed a faint, persistent hiss in their data, a signal that seemed to be coming from all directions in the sky. Initially puzzled by this mysterious signal, Penzias and Wilson considered various explanations, from interference from nearby cities to droppings from pigeons roosting in their antenna. However, none of their attempts to eliminate the signal were successful. The hiss persisted, a faint but unmistakable echo from the early universe. Unbeknownst to Penzias and Wilson, a team of physicists at Princeton University, led by Robert Dicke, had been working on a theory predicting that the Big Bang should have left behind a faint afterglow of radiation, a cosmic background radiation, permeating the universe. This radiation, they predicted, would have been emitted when the universe was about 380,000 years old, at the time of recombination, when electrons combined with atomic nuclei to form neutral atoms, allowing light to travel freely through space. The discovery of the cosmic microwave background radiation, CMB, by Penzias and Wilson, later confirmed by the Princeton team and subsequent observations, provided strong support for the Big Bang theory. The CMB, with its characteristic temperature of about 2.7 Kelvin, minus 455 degrees Fahrenheit, is a snapshot of the early universe, a faint afterglow of the Big Bang that has been traveling through space for billions of years, carrying valuable information about the conditions of the universe in its infancy. The Big Bang theory has become the cornerstone of modern cosmology, providing a compelling explanation for the origin and evolution of our universe. However, while the Big Bang theory successfully explains a wide range of observations, from the expansion of the universe to the abundance of light elements, it is not without its limitations. The theory leaves several fundamental questions unanswered, particularly about the very early universe, pushing the boundaries of our current understanding of physics. One of the most significant limitations of the Big Bang theory is its inability to describe the conditions at the very beginning of the universe, at the moment of the Big Bang itself. According to the theory, the universe originated from an extremely hot, dense state, often referred to as a singularity. However, our current understanding of physics based on Einstein's theory of general relativity breaks down at such extreme densities and temperatures. General relativity, which describes gravity as the curvature of space-time, predicts a singularity at the Big Bang, a point of infinite density and zero volume, where the laws of physics as we know them cease to operate. To understand the conditions of the very early universe, physicists believe we need a theory that unifies general relativity, which governs the large-scale structure of the universe, with quantum mechanics, which describes the behavior of matter and energy at the subatomic level. Such a theory, often referred to as a theory of everything, would provide a framework for understanding the universe at its most fundamental level, including the extreme conditions of the Big Bang. Despite decades of research, a complete theory of quantum gravity remains elusive. However, physicists are exploring various promising avenues, such as string theory and loop quantum gravity, which attempt to unify the fundamental forces of nature and provide a consistent description of the universe at the Planck scale, the smallest possible unit of space and time, where quantum effects become dominant. Unlocking the secrets of the very early universe, the realm where gravity and quantum mechanics intertwine, remains one of the most profound challenges and exciting frontiers in modern physics. The Big Bang theory, for all its explanatory power, leaves us teetering on the precipice of the unknown, the very instant of the universe's birth. At this moment of cosmic genesis, our current understanding of physics falters, unable to penetrate the veil of extreme densities and temperatures that prevailed in the nascent universe. The elegant equations of general relativity, describing gravity as the curvature of space-time, break down when confronted with the infinitesimal scales and quantum phenomena that govern the subatomic realm. This clash between general relativity, the reigning theory of gravity, and quantum mechanics, the enigmatic dance of particles at the smallest scales, lies at the heart of one of the most profound mysteries in modern physics, the nature of the very early universe. General relativity, describing the universe on cosmic scales, excels in predicting the behavior of planets, stars, and galaxies, while quantum mechanics unveils the bizarre and counterintuitive world of atoms and subatomic particles. Yet, these two pillars of modern physics, though remarkably successful in their respective domains, seem incompatible when applied to the extreme conditions of the Big Bang. The incompatibility between general relativity and quantum mechanics stems from their fundamentally different approaches to describing the universe. General relativity portrays gravity as a smooth, continuous curvature of space-time, while quantum mechanics describes the universe as inherently discrete and probabilistic, with energy and matter existing in quantized states. This fundamental difference in their frameworks leads to conflicting predictions when applied to the extreme conditions where both gravity and quantum effects are significant, such as the singularity at the Big Bang or the heart of a black hole. The pursuit of a unified theory, a theory of everything that harmoniously blends general relativity and quantum mechanics, has become a holy grail for physicists. Such a theory would hold the key to unlocking the secrets of the very early universe, allowing us to peer beyond the singularity at the Big Bang and understand the quantum processes that governed the universe's birth. In the absence of a complete theory of quantum gravity, physicists have turned to the intriguing realm of quantum cosmology, seeking to apply the principles of quantum mechanics to the universe as a whole. Quantum cosmology, though speculative, offers tantalizing glimpses into the possible nature of the very early universe, suggesting that the universe may have originated not from a singularity, but from a quantum fluctuation, a spontaneous emergence from a realm beyond our conventional understanding of space and time. One of the most intriguing ideas in quantum cosmology is the concept of the universe as a quantum fluctuation. Quantum mechanics tells us that even seemingly empty space, the vacuum, is not truly empty, but rather a seething sea of virtual particles popping in and out of existence, governed by Heisenberg's uncertainty principle. These ephemeral particles, borrowing energy from the vacuum for fleeting moments, are a testament to the inherent fuzziness of the quantum world, where even nothingness is not entirely nothing. Could our entire universe, with its vast expanse of stars, galaxies, and life itself, have originated from such a quantum fluctuation, a spontaneous emergence from the vacuum of a pre-existing reality? The idea, though seemingly fantastical, is not entirely implausible within the framework of quantum mechanics. If the total energy of the universe, including the positive energy of matter and radiation and the negative energy associated with gravity, sums to zero, a concept known as zero-energy universe, then the universe's creation from a quantum fluctuation would not violate the law of conservation of energy. Quantum cosmology, with its exploration of the universe as a quantum system, challenges our classical intuitions about the nature of reality, suggesting that the universe may have sprung from a realm beyond our conventional understanding of space, time, and even nothingness itself. While still speculative, quantum cosmology offers a tantalizing glimpse into the possibility that our vast and complex universe might be just one of many quantum possibilities, a cosmic bubble in a vast multiverse of possibilities. The idea of a multiverse, a vast ensemble of universes existing alongside our own, was once relegated to the realm of science fiction, a concept more at home in comic books and fantasy novels than in scientific journals. However, recent developments in cosmology and theoretical physics, particularly in the study of cosmic inflation, have propelled the multiverse hypothesis from the fringes of scientific speculation to a serious contender for describing the true nature of reality. Cosmic inflation, a theory proposed in the early 1980s, suggests that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. This rapid expansion, driven by a hypothetical field called the inflaton field, elegantly solves several puzzles in standard Big Bang cosmology, such as the remarkable uniformity of the cosmic microwave background radiation and the flatness of the observable universe. However, inflation, if true, has far more profound implications than initially imagined, suggesting the possibility of a vast and ever-expanding multiverse. According to many inflationary models, inflation is not a one-time event but rather an eternal process, continuing indefinitely in some regions of a larger multiverse. In these regions, the inflaton field continues to drive exponential expansion, creating vast stretches of space-time. However, in certain regions, quantum fluctuations can cause the inflaton field to decay, ending inflation and triggering a hot Big Bang, leading to the formation of a bubble universe like our own. This process of bubble universe formation, driven by eternal inflation, can occur repeatedly and indefinitely, giving rise to a vast multiverse, a tapestry of bubble universes embedded in a larger, ever-inflating space-time. Each bubble universe, born from its own Big Bang, could have its own unique set of physical laws, constants, and even dimensionality, depending on the specific details of how inflation ended in that region. The concept of a cyclic universe, a cosmos undergoing cycles of birth, death, and rebirth, has captured the imaginations of philosophers and cosmologists for centuries. Ancient myths and cosmologies often incorporated cyclical themes, envisioning the universe as eternally recurring, with periods of creation followed by destruction, only to be reborn anew. In modern cosmology, the idea of a cyclic universe has found new life, with theoretical models suggesting that our universe may not be the first nor the last, but rather a single chapter in an eternally repeating cosmic story. One of the earliest modern proponents of a cyclic universe was Albert Einstein himself. Dissatisfied with the idea of a universe with a definite beginning and end, Einstein explored the possibility of an oscillating universe, a cosmos that expands and contracts in an eternal cycle. In this model, the Big Bang is followed by a big crunch, a period of contraction where gravity eventually halts the universe's expansion and pulls everything back together into an extremely hot, dense state, similar to the conditions at the Big Bang. This big crunch, in turn, could trigger another Big Bang, igniting a new cycle of cosmic expansion and contraction. However, simple oscillating models face a significant challenge: the second law of thermodynamics. Entropy, the measure of disorder in a system, always increases over time, at least in a closed system. If the universe were truly cyclical, each cycle should inherit the entropy of the previous cycle, leading to progressively longer and more entropic cycles. This would imply that our current cycle, far from being eternal, is merely a late stage in an ever-lengthening series of cycles, a concept known as the thermodynamic heat death of the universe. To address the entropy problem, more sophisticated cyclic models have been proposed. These models often incorporate mechanisms for resetting entropy at the end of each cycle, either by expelling entropy into a higher dimensional space, or by invoking processes that effectively erase the entropy of the previous cycle, allowing for a fresh start with each new Big Bang. As we delve deeper into the mysteries of the cosmos, we encounter a profound and perplexing puzzle: the apparent fine-tuning of the universe for the emergence of life. The universe, as revealed by modern physics, appears to be remarkably fine-tuned for life, with the fundamental constants of nature and the initial conditions of the Big Bang finely balanced within an exceedingly narrow range that allows for the existence of stars, planets, and ultimately, life as we know it. Consider, for example, the strength of the electromagnetic force, which governs the interactions between charged particles. If this force were just a few percent stronger or weaker, stars would not burn as they do, and the heavier elements essential for life, forged in the fiery hearts of stars, would be absent. Similarly, the strength of gravity, the force that holds galaxies and solar systems together, plays a crucial role in the formation of stars and planets. A slight tweak in the strength of gravity, and the universe might be filled with only black holes or diffuse gas clouds, leaving no room for the complexity and diversity we observe. This apparent fine-tuning with multiple parameters seemingly adjusted within a razor-thin range to allow for our existence, has led some physicists and philosophers to invoke the anthropic principle as a possible explanation. The anthropic principle, in its essence, states that the observed properties of the universe must be compatible with the existence of observers, namely us. In other words, we observe a universe fine-tuned for life, because if it were not so fine-tuned, we would not be here to observe it. The anthropic principle, while seemingly tautological, can be interpreted in different ways. Some view it as a statement of observer selection bias, suggesting that our existence in a life-friendly universe is simply a matter of chance, a consequence of the vast number of possible universes that could exist. Others see the anthropic principle as pointing towards a deeper underlying principle, or theory, that explains why the universe is the way it is, a theory that goes beyond our current understanding of physics. Our exploration of the cosmos, from the ancient myths to the mind-boggling theories of modern cosmology, can leave us feeling both humbled and exhilarated. Humbled by the sheer vastness of the universe, its unimaginable scales of space and time dwarfing our everyday experiences. Exhilarated by the realization that we, as products of this universe, are intricately connected to its grand cosmic narrative, our very existence a testament to the extraordinary processes that have unfolded over billions of years. The atoms that make up our bodies, the oxygen we breathe, the calcium in our bones, the iron in our blood, all were forged in the fiery hearts of stars long ago, scattered across the cosmos in spectacular supernova explosions, the death throes of stellar giants seeding the interstellar medium with the building blocks of planets and life. We are, in a very real sense, children of the stars, our origins inextricably linked to the cosmic cycles of stellar birth, life, and death. This profound connection to the cosmos is not merely a poetic metaphor. It is a scientific reality revealed by astrophysics and cosmology. The processes of stellar nucleosynthesis, the forging of heavier elements from lighter ones through nuclear fusion in the cores of stars, are responsible for creating the elements that make up our world and ourselves. Without the life and death of countless stars scattered across billions of years and vast cosmic distances, our planet and the life it sustains would not exist. This realization, that we are stardust, products of a universe far grander and more ancient than we can fully comprehend, can evoke a sense of awe and wonder, a profound appreciation for the interconnectedness of all things. It reminds us that we are not isolated beings on a lonely planet, but rather integral parts of a vast and intricate cosmic web, woven together by the threads of gravity, time, and the fundamental laws of physics. In 1990, as the Voyager 1 spacecraft, having completed its grand tour of the outer solar system, was about to leave our planetary neighborhood and venture into interstellar space, the famed astronomer Carl Sagan requested that NASA turn the spacecraft's camera back towards Earth one last time. From a distance of about 3.7 billion miles, Voyager 1 captured a poignant image of Earth, a tiny pale blue dot suspended in a beam of sunlight, a mote of cosmic dust against the vast backdrop of space. This iconic image, dubbed the pale blue dot, serves as a stark reminder of our planet's isolation and fragility in the grand scheme of the cosmos. From such a distant vantage point, Earth appears as a tiny, insignificant speck lost in the immensity of space. Yet this pale blue dot is home to all that we know and love, all of human history, all of life as we know it, confined to a thin, fragile biosphere clinging to the surface of a rocky planet orbiting an average star in an ordinary galaxy. The pale blue dot image underscores the preciousness of our planet, the only known haven for life in a vast and seemingly inhospitable universe. It highlights the interconnectedness of all life on Earth, sharing this fragile oasis in the cosmic desert. And it serves as a powerful call for planetary stewardship, a reminder that we must cherish and protect our pale blue dot, for it is the only home we have. The vastness of the cosmos, with its billions of galaxies, each containing billions of stars, may make our planet seem insignificant in comparison. However, this cosmic perspective also underscores the uniqueness and importance of Earth. As far as we know, Earth is the only planet in the universe where life has taken hold, where consciousness has emerged, where beings capable of contemplating their own existence and the mysteries of the cosmos have evolved. Astronauts who have had the privilege of viewing Earth from space often describe a profound shift in perspective, a cognitive and emotional experience known as the overview effect. Seeing our planet from afar, suspended in the blackness of space, a vibrant sphere of life against the stark lunar landscape or the swirling clouds of a distant storm, evokes a sense of awe, interconnectedness, and a deep appreciation for the fragility of our planetary home. Edgar Mitchell, an Apollo 14 astronaut who walked on the moon in 1971, described the overview effect as a sudden global consciousness, a people orientation, an intense dissatisfaction with the state of the world, and a compulsion to do something about it. This profound shift in perspective, common among astronauts who have experienced Earth from space, highlights the transformative power of seeing our planet from a cosmic vantage point. The overview effect underscores the interconnectedness of all life on Earth, transcending political boundaries, cultural differences, and the artificial divisions that often separate us. From space, there are no borders, no conflicts, only a single interconnected biosphere, a fragile web of life sustained by a thin atmosphere and the delicate balance of nature. This cosmic perspective, often described as a sense of the oneness of humanity and our planet, can have a profound impact on how we view ourselves and our place in the universe. It can inspire a sense of responsibility for our planet and its inhabitants, a desire to protect this fragile oasis of life in a vast and indifferent cosmos. The cosmic perspective, humility and responsibility. Contemplating the cosmos, from the Big Bang to the multiverse, can be both humbling and empowering. Humbling because it reminds us of our infinitesimal place in the grand scheme of things, a single species on a tiny planet orbiting an average star in a vast and ancient universe. Empowering because it reveals our remarkable capacity for understanding, our ability to unravel the mysteries of the cosmos and our place within it. This cosmic perspective, this awareness of our interconnectedness with the universe and our responsibility for our actions, can serve as a guiding principle for how we live our lives and shape our future. It can inspire us to act with greater compassion, understanding, and a sense of shared destiny, recognizing that our actions have consequences not only for ourselves, but for future generations and the planet we share. The challenges facing humanity, climate change, resource depletion, social injustice, can seem daunting, even insurmountable, when viewed from our limited terrestrial perspective. However, the cosmic perspective offers a different lens through which to view these challenges. It reminds us that we are not alone, that we are part of a larger cosmic story, and that our actions have the potential to shape the future of life on Earth, and perhaps beyond. Embracing the cosmic perspective does not require abandoning our earthly concerns or denying the importance of our everyday lives. Rather, it invites us to view those concerns through a wider lens, recognizing that our actions have implications that extend far beyond our immediate surroundings. It encourages us to act with greater humility, recognizing our place within a vast and interconnected web of life, and with greater responsibility, understanding that the choices we make today will shape the world we leave behind. Our cosmic journey continues. Exploring the infinite frontier. Our exploration of the cosmos is far from over. The more we learn about the universe, the more we realize how much remains unknown, how many mysteries still beckon us to unravel their secrets. From the nature of dark matter and dark energy, the invisible forces shaping the universe on the largest scales, to the possibility of life beyond Earth, the cosmos continues to ignite our imaginations and challenge our understanding. New telescopes, both on Earth and in space, are being built with ever-increasing power and sensitivity, peering deeper into the cosmos, capturing fainter light from more distant objects and revealing the universe in greater detail than ever before. Spacecraft are venturing farther into our solar system, exploring planets, moons, and asteroids, searching for clues about the origins of our solar system and the potential for life elsewhere. The search for extraterrestrial intelligence, though yet to yield definitive proof of life beyond Earth, continues to captivate our imaginations and fuel our desire to know whether we are alone in the universe. The discovery of even a single microbe on a distant planet or moon would revolutionize our understanding of life's place in the cosmos, demonstrating that life is not a cosmic fluke, but rather a fundamental property of a universe teeming with possibilities. Our cosmic journey is a testament to the indomitable human spirit, our innate curiosity and thirst for knowledge driving us to explore the unknown, to push the boundaries of understanding, and to unravel the mysteries of the cosmos. As we continue to explore the infinite frontier, we carry with us the lessons learned from our ancestors, the insights of countless scientists and explorers, and the profound realization that we are all connected, children of the stars bound together on this pale blue dot, our shared cosmic home. Reflections on a cosmic journey. As we conclude our exploration of the cosmos, from the Big Bang's fiery genesis to the profound implications of the multiverse, we are struck by the remarkable journey of human understanding. From the earliest myths and legends, whispered around campfires beneath a canopy of stars, to the sophisticated theories of modern cosmology, born from centuries of observation, experimentation, and mathematical rigor, our quest to comprehend the universe has been a testament to the boundless potential of the human spirit. The journey has been marked by both profound insights and enduring mysteries. We have uncovered the fundamental laws governing the cosmos, from the subatomic realm to the grandest cosmic scales, revealing a universe more vast, more complex, and more awe-inspiring than anything our ancestors could have imagined. We have traced the evolution of the universe from its fiery birth to the formation of stars, galaxies, and planets, culminating in the emergence of life on our own pale blue dot. Yet, for all that we have learned, the universe retains its capacity to surprise and humble us. The very beginning of the universe, the moment of the Big Bang itself, remains shrouded in mystery, hidden behind a veil of Planck-scale physics where our current theories break down. The nature of dark matter and dark energy, the invisible forces shaping the universe on the grandest scales, continues to elude our grasp. And the question of whether we are alone in the universe, whether life has emerged elsewhere among the billions of galaxies, each teeming with billions of stars, remains one of the most profound and unanswered questions in science. Our exploration of the cosmos has not only expanded our understanding of the universe, but has also profoundly altered our perspective on ourselves. It has revealed our interconnectedness with the cosmos, the ancient origins of the atoms that make up our bodies, forged in the fiery hearts of stars long ago. It has highlighted the fragility of our planet, a solitary oasis of life in the vast cosmic desert, and the importance of preserving this pale blue dot for future generations. Our place in the cosmic order. The cosmic perspective, this awareness of our place in a universe far grander and more ancient than we can fully comprehend, can be both humbling and empowering. It humbles us by revealing our infinitesimal size and fleeting existence in the grand scheme of things. It empowers us by reminding us that we are part of something much larger than ourselves, participants in a cosmic story that has been unfolding for billions of years. This cosmic perspective can serve as a guiding principle for how we live our lives and shape our future. It encourages us to act with greater compassion, understanding, and a sense of shared destiny, recognizing that our actions have consequences not only for ourselves, but for future generations and the planet we share. It inspires us to strive for a more just and sustainable world, one that recognizes the interconnectedness of all life and the importance of preserving the delicate balance of nature. The challenges facing humanity, Climate change, resource depletion, social injustice can seem daunting when viewed from our limited terrestrial perspective. However, the cosmic perspective offers a different lens through which to view these challenges. It reminds us that we are not alone, that we are part of a larger cosmic story, and that our actions have the potential to shape the future of life on Earth, and perhaps beyond. As we continue our exploration of the cosmos, we carry with us the lessons learned from our ancestors, the insights of countless scientists and explorers, and the profound realization that we are all connected, children of the stars, sharing this pale blue dot, our cosmic home. The journey of cosmological exploration, from the earliest myths to the most sophisticated theories of modern science, has been a testament to the power of human curiosity, our innate desire to understand the universe and our place within it. And as we venture further into the cosmos, we do so with a sense of wonder, humility, and a deep appreciation for the vastness, beauty, and mystery of the universe we inhabit.